Suppose you try to push a wagon and a car with the same amount of force. How will their motions be different? Newton's laws of motion can describe how the wagon and car will move. Hi, and welcome back. In today's science episode, I will talk about Newton's laws of motion.
Newton's laws of motion. Isaac Newton and the laws of motion. In 1665, Cambridge University in Britain closed for 18 months because of the bubonic plague. Isaac Newton, a 23-year-old student, used this time to develop the law of universal gravitation, calculus, and three laws describing how forces affect the motion of objects. Newton's laws of motion apply to the motion of everyday objects, such as cars and bicycles, as well as the motion of planets and stars. So, if Isaac Newton developed the law of universal gravitation during a quarantine, what have you done during this quarantine so far? Moving on, people. Newton's first law of motion. Newton's first law of motion states that an object moves at a constant velocity unless an unbalanced force acts on it. This means that a moving object will continue to move in a straight line at a constant speed unless an unbalanced force acts on it. If an object is at rest, its velocity is zero, and it stays at rest unless an unbalanced force acts on it. Inertia. Newton's first law is sometimes called the law of inertia. Inertia is the tendency of an object to resist any change in its motion. The picture shows a toy car hitting a block and stopping. The block on top of the car is not attached to the car and keeps traveling. The block's forward motion demonstrates the property of inertia. Inertia and mass. Does a bowling ball have the same inertia as a table tennis ball? Why is there a difference? You could not change the motion of a bowling ball much by swatting it with a table tennis paddle, but you could easily change the motion of the table tennis ball. A greater force would be needed to change the motion of the bowling ball because it has greater inertia. Recall that mass is the amount of matter in an object. An object's inertia is related to its mass. The greater an object's mass is, the greater its inertia is. A bowling ball has more mass than a table tennis ball has, so the bowling ball has a greater inertia. You will sometimes hear people say that when an object begins to move, inertia is overcome. This is not true. The object still has mass when it's moving, so it still has inertia. As long as the mass is the same, the object has the same inertia. Newton's second law of motion. Newton's first law of motion states that the motion of an object changes only if an unbalanced force acts on the object. Newton's second law of motion describes how the forces exerted on an object, its mass, and its acceleration are related. Force and acceleration. How are the throwing a ball as hard as you can and tossing it gently different? When you throw hard, you exert a greater force on the ball. The ball has a greater velocity when it leaves your hand. The hard-thrown ball has a greater change in velocity, and the change occurs over a shorter period of time. Recall that acceleration equals the change in velocity divided by the time it takes for the change to occur. So, a hard-thrown ball is accelerated more than a gently thrown ball. Mass and acceleration. If you throw a softball and a baseball as hard as you can, as shown in Figure 3, why do they not have the same speed? The difference is due to their masses. A softball has a mass of about 0.20 kilograms, but a baseball's mass is about 0.14 kilograms. The softball has less velocity after it leaves your hand than the baseball does, even though you exerted the same force. So therefore, the softball has a smaller final speed because it experiences a smaller acceleration. The acceleration of an object depends on its mass as well as the force exerted on it. Force, mass, and acceleration are related. Relating force, mass, and acceleration. Newton's second law of motion states an object's acceleration is in the same direction as the net force on the object and is equal to the net force exerted on it divided by its mass. Newton's second law can be written as the following equation: acceleration equal net force divided by mass. In the above equation, acceleration has units of meters per second square, and mass has units of kilogram. Recall that the net force is the sum of all the forces on an object. Remember that the SI unit for force is a Newton and that 1 Newton equals 1 kilograms times meter per second square. Just like velocity and acceleration, force has a size and a direction. Calculating net force. Newton's second law can also be used to calculate the net force if mass and acceleration are known. To do this, the equation for Newton's second law must be solved for the net force. To solve for the net force, multiply both sides of the above equation by the mass. The mass on the right side cancels. For example, when a tennis player hits a ball, the racket and the ball might be in contact for only a few thousandths of a second. Because the ball's velocity changes over such a short period of time, the ball's acceleration could be as high as 50,000 meters per second square. The ball's mass is 0.06 kilograms, so the size of the net force exerted on the ball will be 300 newtons. And here is how we solve it. We just apply the formula. Let's do an example problem. Solve for acceleration. You push a wagon that has a mass of 12 kilograms. If the net force on the wagon is 6 newtons south, what is the wagon's acceleration? Identify the know. What we need to find? The acceleration. List the knowns. What things do we know so far? We have the mass, that is 12 kilograms. We have the net force, 6 newtons south. So now we just need to apply the formula. My answer will be 0.5 meters per second square. Let's check the answer. The value of the net force is 6 is less than the value of the wagon's mass, 12. So we would expect the acceleration value to be less than 1. So our answer, 0.5 meters per second squared, makes sense. Newton's third law of motion. What happens when you push against a wall? If the wall is sturdy, nothing happens. But if you push against a wall while wearing roller skates, you would go rolling backward. This is a demonstration of Newton's third law of motion. Newton's third law of motion states that when an object exerts a force on a second object, the second object exerts a force on the first that is equal in strength and opposite in direction. Sometimes Newton's third law is written as, to every action force there is an equal and opposite reaction force. However, one force is not causing the second force. They occur at the same time. It does not matter which object is labeled object 1 and which is labeled object 2. Think about a boat tied to a dock with a taut rope, like the one in the picture. You could say that the action force is the boat pulling on the rope and the reaction force is a rope pulling on the boat. But it would be just as correct to say that the action force is the rope pulling on the boat and the reaction force is the boat pulling on the rope. Forces on different objects do not cancel. If these two forces are equal in size and opposite in direction, you might wonder how some things ever happen. For example, if the box in figure 4 pushes on a student when the student pushes on the box, why does the box move? According to the third law of motion, action and reaction forces act on different objects. Recall that the net force is the sum of the forces on a single object. The next picture in figure 5 shows the forces on the student. The net force is 0, and the student remains at rest. The right picture shows that there is a net force of 20 newtons to the right on the box, and the box accelerates to the right. Forces are interactions. Newton's third law states a very important fact. Forces are interactions between objects. For examples, it makes no sense to say, the box has a force of 30 newtons. Is this force acting on the box? Is the box pushing on something? What is causing this force? It makes sense, however, to say the student applied a force of 30 newtons to the box. Look at the skaters in figure 5. The male skater is pulling upward on the female skater, while the female skater is pulling downward on the male skater. The two forces are equal in size but opposite in direction. Both skaters feel a pull of the same size.
I hope you found this video useful. Thanks for watching and until the next one. Bye!